OK. Bonjour tout le monde. Welcome, everyone. Thank you for coming. Merci d'être venu. So we are week 11. And today I will discuss dynamical mean field theory. I will not finish completely today, but the main part. And we could spend much more time on this, but I will instead move to broken symmetry. Okay, so last time we derived this two-particle self-consistent approach, and the spin. So the spin fluctuations, there are three. A spin flip, when you have a spin wave, it has quantum numbers s equals 1, so it has three components. So that's in a sense why there is a 3 here, but there's only 1 here. And we said that this satisfies 1/4 of the sum rule, and then 3/4 for this one. The sum rule being relating sigma g to un up and down. Okay, so the other result that we found is that this self-energy, the imaginary part of the self-energy at 0 frequency on a hotspot, that is 2 points that can be linked by the antiferromagnetic wave vector, or the fluctuation that is doing that is dominant, goes like c to the 3 minus d divided by c thermal, where c thermal is V Fermi over T. And so that led to pseudo gap and hotspot. Now, one limitation of this approach is that it's not valid when U is very large. It's always based, in some sense, on U being less than the bandwidth. But there are some interesting phenomena that happen when U is larger than the bandwidth, and that's what we're going to discuss today. So are there any questions before I go on? Okay, so you interrupt me anytime. So one of the problems that faced solid state physics already when it started, like in the 1920s, then in 1937, it was noticed that there were some experiments on nickel oxide, where if you just count the number of electrons and use band theory, you expect that this will be a metal, but it was an insulator. So the experiments were done by De Boer or some, and the Piles and Mott at that time in 1937 noted that maybe it was because the interaction was too strong to to allow the electrons to move. So you had a half-filled band, which means that let's say you have a lattice here, and the half-filled band is, you have one electron per conduction electron, one electron per site. So at that filling, if you want to move, you have to, there's a strong repulsion on atoms, and at some point this will not move. So you can see this. I will share my screen. What happened to? Sorry, I had a problem with my system failed just before we started. So okay. Okay, so this is a phase diagram of temperature, and then you can think of this as pressure. In fact, it is pressure. Yeah. On this axis, it's not pressure, it's doping with titanium and chromium, which is equivalent of a chemical pressure. So this is vanadium oxide. And the point is that you see that at large pressure, there's a ground state that's antiferromagnetic. And then if you increase the temperature, you get a metal. So the type of theories we have discussed up to now would be happy with that. So in the antiferromagnetic state, it's an insulator, but it's because the unit cell is twice as large. And so in fact, you have a filled band. But as soon as the antiferromagnetism disappears, you get a metal. So that was the point of view of Slater. But you see that in this region, if you go above the transition temperature for the antiferromagnet, you get an insulator. And it's a paramagnetic insulator. In other words, there's no long-range order here. It's just this half-filled band, but insulating. And it's adiabatically connected to the metal. In other words, there's a first-order transition here between insulator and metal, but it ends at a critical point, like in the phase diagram of water, and you can go from metal to insulator by going around this point. So that's what we want to explain here. What happens? Why can we have a first-order transition between an insulator and a metal without changing the lattice parameters or without changing the size of the Brillouin? So we will see the predictions of this theory, how it's related to what I showed you. But the best solution to this was found by dynamical mean field theory. So it's always nice to have some control parameter when you do theory. And sometimes this control parameter is rather artificial, but it ends up working in practice. So here it turns out that this theory is exact in infinite dimension. D equals infinity. So the first thing is that you see that when D is large here, then this is a negative here, this exponent. So basically, the self-energy at the zero temperature will go to zero. So in other words, there's no special point on the Fermi surface. These hot spots disappear. So what we expect then, and that's the self-energy in infinite dimension, is that the self-energy in infinite dimension will depend only on frequency. Here I wrote Matsubara frequencies, but depends only on frequency. So how can we justify this a little bit, the fact that it depends only on frequency? Well, take C dagger I, Cj, okay? One way to think of this is that it is the overlap between the many-body wave function that has one less electron on site J. And here you can think of this as acting this way. Then it's the wave function, many-body wave function with one less electron on site I. Now, if you look at this, then psi I, psi J square, you can interpret this as the probability that if you remove an electron on site J, that this will propagate on site I. Now, if you think of current conservation, okay, then you have you're in 2 dimensions here. And then in 3 dimensions, you have this, and then you go to higher dimension, 4, etc. You see that this has to scale like 1 over the dimensionality, because I have 1 electron, and it has 2D places to go, where D is the dimension. It can go left, right, that's 2, then 4, and then 6, and so on. So there are more rigorous proofs of this, but I think this is quite intuitively correct, right? It has less chances. I mean, if you take a particular site I here, so this is J, and this is I. If you are in high dimension, it has less chances of going here, and it would go like 1 over D. So that means that this object here goes like 1 over square root of dimension. And that was Metzner and Balhart who figured this out. Now, why is this helpful? Look at the self-energy. So if we want to know the self-energy at site I, there's no problem. I mean, we know how to do this. And then we go like this, but this is U, it's at the same site. So we have the Green's function at the same site. And then look at one higher order diagram. For example, this. Okay. Now, if I go from I to J, where J is not equal to I, even if these are first neighbor, the Green's function that are in this will go like 1 over square root of D, right? And I have 3 Green's function. So this is 3. So it goes like 1 over D to the 3f. And you see that if I continue here to any higher order, this will go down always. On the other end, if I stay on site I here, if I go I, then I don't have this factor. So in D infinity, all I need to do is to sum this series to infinite order, where the only thing that comes in is the Green's function at that is at site I. So the time here can be different. There's no problem with the time, but the location, in space, it's local. And if we remember the lesson from TPSC, then it's not surprising that in infinite dimension, sigma depends only on frequency. Because remember, even though there are site labels like this, there's also a time label. And the time or the frequency is not constrained. So, then the result then is that in infinite dimension, if we know the local Green's function, okay, what is the local Green's function? Gii of ikm is equal to integral d dk over 2 pi to the d times e to the I k dot 0 times 1 over ikm minus epsilon k minus mu minus sigma of ikm. Okay, why I put 0 here? Because what comes in usually is the distance between these 2 points. Okay, and here the distance is 0. Is that clear? Is that okay? So it means that I get 1 here. So you see, you have a self-consistency. Suppose you have some self-energy, then you can compute this. You get this guy. Now, once you have this, This is the Green's function that goes everywhere. Yeah. So I can compute a new self-energy, and I can put it back here, get a new G, and you see I have a self-consistent problem. But this is not the way it's done in practice. You know, if there was a simple way to sum this series with this, then that will be it. But in practice, we have some non-interacting propagator, non-interacting Green's function, and we compute the self-energy to infinite order. So another way to look at this is to say that suppose, and I will show you we can do this. Suppose I can, so I can do GII to the minus 1 of IKN is equal to G0 to the minus 1 II of IKN minus sigma of IKN. Then this is the thing I should compute self-consistently. Okay. But we don't know yet that I can do this, so I will show you. So we've discussed this, and we've discussed the self-consistency. That's the first way to look at it.
So you're saying we're trying to compute G0 self-consistently?
So it's the G0 minus 1 that we will compute the self-consistently, yes.
Okay.
But as I say, if there is a way to do, given this, if there's a way to do this sum and compute the self-energy exactly with this, then we can do the self-consistent problem just like this. Okay, I start with G, I sum some random sigma that I hope is the right answer. I do this, I get some result for the self-energy, which is not the same I had before, so I put it there. I get a new GII, and then okay, I could iterate this way. Okay. But in practice, what I'm saying is that what we have is a non-interacting Green's function, this G0. And as I said, it's not obvious that we can write it like this, but I will show you that we can. And the way is to look at this so-called quantum impurity model, or Anderson model, Anderson impurity model. So the result would be that to solve this problem like this in infinite dimension, what we need to solve is an Anderson impurity problem. So you see what will happen is that, okay, this is justified in infinite dimension, but the approximation will be to do that in finite dimension. And it turns out that in practice, d equals 3 is not really far from infinity. But d equals 2 we saw is not the case. And d equals 2, you have some momentum dependence. Okay. So what is the Anderson impurity model? So this quantum impurity or Anderson impurity model. And I forgot to mention, we're always solving the Hubbard model here, okay? So the U is local. So we have some conduction band. So we have electrons that hop from one side to the other. And we can put some electrons. They are free electrons. It's a conduction band. They are free electrons. And then there is one site I, where you have, let's say you have an F electron. Usually this was, people had in mind the heavy fermions, or looking at the F electrons. So you have a very localized impurity here that has a spin, and there's a U on that. There's no U on this. There's only U on this. And then there's some hybridization between these two sites. So not only the electrons can hop here from one side to the other, but they can also hop with this. Okay. So because of the U, then this will this usually will be singly occupied. Normally, you see there would be two electrons that would fall here, but because of the repulsion, it's not the case. So let's write the Hamiltonian for this. So let's write K is H minus mu m. And what is H? So H as a Hamiltonian for the conduction band, one for the F here, and there is this hybridization here that allows us to go from here to there. Is that okay? So let's write this down then. So H conduction is just the sum. I will write. Now I will N includes this, the conduction electron and the F electron. So I will write. So I will write K. K for the conduction electrons is sum over K sigma of epsilon K minus mu C dagger K sigma CK sigma. Okay, simple. Now for the F electron, so Kf then is sum over sigma. It has some energy epsilon. This was a band energy, but now this is another energy epsilon minus mu times F dagger at site I spin sigma F at site I times sigma. So we call this the site I, or if you want, the impurity site. And then we have plus U and F up and F down. Okay, so that's the number of F electrons up times the number of F electrons down. So that's the only site that has an interaction. And now we write, I will have space problems, but okay, let me write it here. So the hopping between conduction band and F electron is equal to sum over K sigma. Okay. What I will do is to sum over all wave vectors. So the K, if I sum C dagger K over all wave vectors, it will give me C at this site, right? You know how that works. The creation operator at this site is just the sum over all K of e to the ik dot r times C of K, but r is 0, so it's just the integral over K. So it would be V Ki C dagger K sigma F sigma plus V star Ki F dagger sigma Ck sigma. Okay, you see why I did that, because V is something related to this hopping here. It's possible that not all K vector couple the same way to this. So I keep it as general as possible. So the sum of all these terms is the Anderson impurity model. Okay. So let me write down now the equations. What I want is the Green's function of the F electron, the Green's function on this side, GFF of time tau. So what will be the equation of motion for that? Okay, if I didn't have this term here, it would be IKN minus epsilon minus mu times G FF of IKN is equal, you see why I do that, is equal to 1. Okay, you recognize that's the equation of motion for the non-interacting problem when u is 0. Now, if I add some, now there are two additional complications. There's this, which involves the F as well. And there is this, which involves U. So for U, what we know what we will obtain is the self-energy here. Sigma of IKN. Okay, running out of place. So I have IKN minus, just to save space, let me write this as zeta. So it's zeta is epsilon minus mu, okay? And then I will have minus sigma of IKN. Okay, as usual, you write the equation of motion for this. You need to compute the commutator of the F of these F electrons with the Hamiltonian. So there's a non-interacting part here that comes from here, and so this is the dd tau once it's Fourier transform, and that's the part that comes from the interaction. But now I have something else. There are these terms as well, right? So here the same way I had minus zeta. When I commute the F operator with this, I will get a contribution from this. I think I wrote it backwards in the notes. Okay. So time derivatives of F will give me the commutator of the Hamiltonian with F. So it means I get a contribution from this. Okay. So I will get minus V star K No, I have it correct. Okay, it's here. I will get. So you got now. I'm building a matrix here. So here I have. Let me to be clear. Let me separate this like this. I will have this with a minus sign, just like the zeta. So in the same way that the F dagger F led to this, now the commutator with F dagger, this is also anti-commuting. So that's why it works the same way. So I will have V star Ki. K is the, so now I want to write an infinite matrix, so it's too big for us. So let me take just 3 wave vectors, okay, just to show how it works. So I get VK1 I, and then I have minus V star K2 I, and minus V star K3 I. And you see that when I do this commutation with this, what I get in the end is not a F, it's a C. Okay, when I commute, when I take the equation of motion for the C, with the F operator that's in this Green's function, that's the first one here, I will be left with a C. So that now what these guys do is that they couple to other Green's function, they couple to G C F of IKN and K1. So how K1. And then this one is G C F. You see it's a Green's function here that has FF. This one has C times F. You remember when we derive the equation of motion for the Green's function, there's just the F dagger that's just plugged in to the right to make this thing a Green's function. So here I have IKN K2. And then I have G C F of IKN K3. And that's equal to 1 here. So you have to think of this as matrix multiplication, okay? So if there were, so without this, this is just a non-interacting problem. Okay, now I need to write the equations of motion for the C, okay? So what will happen? When I write the equation of motion for C, there is this diagonal piece here that I will recover. So here I will get IKN minus zeta K1, and that will not be coupled to K2 and K3. There's nothing that couples to K2, K3. So I have 0, 0, and then I have 0, and then I have IKN minus zeta K2, 0, 0, 0, IKN minus zeta K3. But again, when I take the time derivative of the of the C, which is what gave me the IKN. I also get contribution from these guys now. You see the C, when I commute with the C dagger, I will be left with an F, and the F will give me back the GFF. Okay, so here what I have is minus V star K1I minus V star K2I minus V star K3I. I is an index here. Here I put it a little bit too big. And then there's a contribution that comes from the theta function in the definition of the time ordered, right? So now I will get the equal time anti-commutator of C with F, which is 0. Okay, so here I have 0, 0, 0. Okay, I repeat. When I compute the time derivative of the C, there's a term that comes of this Green's function. There's a term that comes from the time order, the differentiating the time ordering operator that gives a delta function and the anti-commutator of C with F, which is 0. Okay, here I add 1. That's different. Okay, so you see what I can do is write an equation of motion for F only. How I do that by eliminating all of these GCF. And how do I do that? So in the notes, I have done all the commutator and anti-commutator and everything. But here I take this shortcut here. You become so expert in the Green's function now. It's not a problem. So you see what I can do here is the following. If I look at this set of equation here down here, what do I have? Let me call this D. Okay, this big matrix. So I have a D that acts on this column vector. Okay. So G, C, F. So that's a vector. That's it's a column vector. Okay, because I have matrix times vector is vector. So take this like this. And then minus, so this is vector times scalar, right? Because every time this multiplies this multiplies that, this multiplies that. So this is just scalar times vector. So this is equal to V star K I times GFF. Okay, you have to think of this as this was a vector in K1, K2, K3, and this is also a vector in K1, K2, K3. Okay, I write that as a shorthand. So it means that GCF, this column vector here, GCF is equal to D, let me write the same symbol, is equal to D minus 1 times V star K I times G F F. Okay, so this matrix here has K1, K2, K3. Okay, labels K1, K2, K3 just like this. But it's a 2 by 2 matrix, but it's diagonal, so it's easy to invert. So it means that now I can, sorry, I make a big mistake here. Here I had V star, but here I had V, right? Because it's the other term I was anti-commuting. I'm really sorry. So this is V. So now I know this guy here. I know this column vector here. So I can write the equation of motion for this this way. I can write IKM minus zeta minus sigma FF. And then I have minus, so this is multiplying this guy, and this guy is equal to this. And we remember that we have sums over K all the time. So it means that this will be sum over K of, so this V star Ki 1 over IKM minus zeta K times V Ki. Okay. D minus 1 is this. It's just inverting this. And K, and then I multiply by K. So this is the so here I had the V star, and here I had D minus 1Z. Okay. So times GFF equals 1. So that's the equation of motion for this guy. And you see this is frequency dependent. And so it's called an hybridization function. So I have delta of IKM is equal, by definition, to sum over k, and that's for one spin species, is equal to sum over k of vki. Okay, this is a scalar, so I can put it here if I want. No. Let me leave it there. This I will write as v dagger ik. Okay, so I switch this and I put the dagger here because I have a star here already. 1 over ikm minus zeta times v ki. And then the equation of motion for GFF is just that ikm minus zeta minus delta of ikm minus sigma ff. I should write the sigma of ikm Sorry, my pen is running out, huh? Look better. Okay, let's start over again. Excuse me. So you see, this is so-called the hybridization function. And now we have the structure that if I call this G0 minus 1, we have the same structure I was talking about earlier. Okay. So now we will proceed in two steps. Well, first let's discuss the physics a little bit. Well, what is the meaning of this delta of IKM? You see, we are summing all the different ways that the particle can go in the vat and come back. It starts at the impurity site I, it ups here, then it travels in the vat, and then in the mode K, in a plane wave K, and then it comes back to the vat. Here I forgot to put the label K. Okay, and we have to sum over all possible ways of doing this. So this is our intuition and quantum mechanics about taking all possible paths. So to go from a given imaginary time to another imaginary time, it means that the electron can either do it as usual, or it can do it by hopping to the vat, this conduction electron band, and then coming back to this vat. So next time I will show you why perturbation theory for the Anderson impurity model, for what we just wrote down, why the perturbation theory is exactly what we had before. And the argument will be that this delta that is here plays the role of this phi that we had before. That if we can show that this delta, see, because this was time dependent too, or frequency dependent, like in this case. If we can show this, then we are done. So that we will do next time. So that's this part here. But now I want to show you how dynamical mean field theory is mapped to this Anderson impurity model. Okay, I will have to erase this. Here in the Anderson impurity model, the BAT, this convection band is given. In dynamical mean field theory, and that's why it's called a dynamical mean field, it will be determined self-consistently. In other words, this function here, delta of IKM, will be an iterative loop. And so we solve this problem of this in a bath of non-interacting electron. And we will see that how I'm going to show you right now what happens to this delta. So here is what we do. Okay. We know that this whole thing is just, if we go back down to the problem of the problem of the dynamical mean field theory. At step number 1, we have a delta. Let's say, I will call it at the nth iteration, delta of IKM. And one way to estimate this, is to take a self-energy that's 0, and then integrate over all wave vectors and get an estimate for the integrate over all wave vectors the non-interacting Green's function for the lattice, and then we get this. Okay, so suppose I'm given this. Okay, so now this is the non-interacting Green's function, and I have not shown you this, but I will. With this non-interacting Green's function, I can compute the self-energy at step n+1. Okay. Now, if I have the self-energy at step n+1, what I can do, I can compute the local self-energy, GFF of IKN, or if you want to make sure that there's no confusion with the Anderson impurity model here, I will go back to GII that I was discussing at the very beginning. So GII of IKN is equal to integral ddk over 2 pi d, and that's at step n+1 times 1 over IKN minus zeta k minus sigma at step n+1 of IKN. You see, I was able to compute this, so I put it there, and then this is the lattice. I'm back to dynamical mean field theory now. So I can, if I integrate over all wave vectors, I get the local Green's function. Now with this local Green's function, what can I do? I can use this basically. So I can see that delta at step n plus 1 is equal to this ikn minus zeta minus what I just obtained here, g I at step n plus 1 of ikn to the power minus 1 minus sigma at step n plus 1 of ikn. Okay, you see, if I put this here, I get this. This is g minus 1, right? This whole thing is the inverse of the local Green's function. So if I put this here and put this to the right, then I get this. Okay. Now, if this is equal to that, I'm done. If this is not equal to that, then I put it back. I put, okay, 5 is what I call delta n now is delta of n plus 1. Okay, and I can loop like this. So the dynamical mean field is this, if you want, or you can think of this as the dynamical mean field as G0 minus 1. One or the other is the same thing. Now there are many methods that have been developed to solve this Anderson impurity model. So that's why this became very popular. And it's also because it gives us the correct physics for the Mott transition that I will discuss the next time. What are the results of this? So now one way to solve this problem, to do this dynamical mean field, is to write down an Anderson impurity model and do exact diagonalization, right? If you write down some Anderson impurity models, do some exact diagonalization, then what you are doing then when you want to update what this delta is, you have some fit parameters for these v's and the zeta here. These are all free parameters that you modify to get a new delta. You started with some parameters that gave you some delta, but you don't need the delta to do the calculation. You just do exact diagonalization for this problem. With exact diagonalization, then you can find the self-energy. Then you can project back. You can get the local Green's function, get a new delta. And now the new delta means you start with a new Anderson impurity problem with new v's and new zeta. So you need some sort of just minimization problem to get a new v and zeta. Now the bat will always be finite if you do exact diagonalization, but if the bat is big enough, then it's fine. Okay, so let's stop here. Any questions? Okay, think about this then, and tomorrow I will show you that indeed this, the problem formulated this way has precisely the same perturbation structure as this, except that what goes in these g's are the local Green's function, in other words, this integral or this thing. Including this, yes. Okay. Okay, so see you Wednesday then. If you have questions, I'll stick around a little bit.
Merci beaucoup.
Bye.